Just look around you for a second. Your lights, your computer, your phone charger. Ever stop and think about what's really happening inside those wires? Electricity. It's this invisible force that powers, well, pretty much our entire world. So, in the next few minutes, we're going to break down exactly what it is, where it comes from, and how it really works.
I mean, we see its most obvious effect as light, right? Electricity just fundamentally changed everything for us by letting us conquer the darkness. It literally extended our days for working, for learning, for connecting with each other.
And then there's heat. It creates this incredibly powerful heat that cooks our food and warms our homes. And this amazing trick, transforming an invisible current into actual thermal energy, it happens right on our countertops every single day. And of course, it creates motion. From little toy cars like this to absolutely massive trains, electricity is the force that gets things moving. So you've got light, heat, and motion, all coming from the exact same invisible source. So that brings us to the big questions, doesn't it? What is this invisible force really? Where does it even come from? And how in the world does it travel from some giant power plant all the way to that little light bulb in your room? Well, let's find out. To really get a handle on electricity, we have to start small. I mean, really small. We're talking about the tiniest, most fundamental particles that make up, well, everything in the entire universe. And here it is, the hero of our story, the electron. You see, everything is made of atoms, and inside those atoms are these tiny little particles. When we can get these electrons to jump from one atom to the next in a continuous stream, that flow, that movement, is what we call electricity. Simple as that. What's really wild is that humans have known about this for a surprisingly long time. We're talking over 2,500 years ago. The Greek mathematician Thales discovered what we now call static electricity just by rubbing some amber with fur. And you know what? The principle is exactly the same as the static cling you find in your laundry today. And this is a perfect example of that connection across millennia. On the left, you've got Thales's experiment. And on the right, a feeling I'm sure is pretty familiar. Going down a plastic slide and having your hair stand right on end. Both of these are caused by the exact same thing. Electrons being physically moved from one surface to another. You can actually see this for yourself. It's a super fun experiment. When you rub a balloon on your hair, you're literally scraping electrons off your hair and onto the surface of the balloon. That gives the balloon a negative charge, which then attracts the little pieces of paper. It's a tiny, totally safe way to see a powerful force in action. Okay, so static electricity is when electrons kind of build up and hang out in one place. But to actually power a light bulb, those electrons need to flow. They need to move. So, how do we make them move on command? Honestly, the best way to picture this is to just think about water. Seriously, imagine the electrons are just little drops of water. The wire they travel through, that's the pipe. And the battery? The battery is the pump. It provides the pressure, which in electricity we call voltage, to push those electrons along and make our lamp, which is like a water wheel, do its job. Now, this is absolutely crucial. The flow needs a complete, unbroken path, kind of like a racetrack. We call this a circuit. If there's a break anywhere in that loop, everything just stops. A light switch? That's really just a simple gate that we use to open or close the circuit on purpose. You can even build a really simple one. The energy flows out of the battery, through one wire, lights up the bulb, and then flows out through the second wire right back to the battery. You've made a complete loop. But the second you disconnect even one of those wires, the light goes out because you've broken the circuit. And check this out. The path doesn't even have to be a wire. This is a squishy circuit, and it uses a special conductive dough to complete the loop. It's just a great, fun example that shows as long as you have an unbroken path for electricity, you can power something up. But wait a minute. That brings up a good question, right? Why can electricity travel through a wire, or that special dough, but not through the plastic that's wrapped around the wire? Well, it's because different materials play by different rules. Let's look at the rules of the road for electrons. So materials pretty much fall into two camps. First, you have conductors, like the copper metal inside a cord. They're like a wide-open freeway for electrons. Then you have insulators, like that plastic coating. They hold onto their electrons super tightly, basically creating a roadblock. And that combination is what makes electricity so useful and safe. The conductor delivers the power, and the insulator protects us from it. So, we get how small circuits work, but how does this scale up to power our entire world? Let's zoom out for a second and take a look at the bigger picture. Well, the electricity in your home comes from these massive generators, and most of them work on a pretty simple principle. Something needs to spin a turbine. That could be steam from a power plant, the force of the wind, or flowing water from a dam. That spinning turbine then turns a generator, which is basically a machine that uses magnets to push electrons into the power lines, sending them on their long journey all the way to you.
Okay, now that we know how it gets to us, we have to talk about safety. Because electricity is so common, a few really dangerous myths have popped up over the years. We're going to tackle a big one right now.
I mean, we use it every single day, so it's really easy to get complacent. A lot of people think the current that runs through a regular wall outlet is maybe too weak to be a real threat. But is that actually true?
This is one of the most persistent and, frankly, dangerous myths out there. This belief that because it's not some high-voltage power line, the electricity in our homes is basically safe to mess with. This could not be more wrong.
The shocking truth is it takes very, very little current to be fatal. An amp is the unit we use to measure that flow of electrons. Your phone charger might use about 1 amp. A fatal shock, though, can happen with as little as 10 milliamps. That's 1/100th of the current from your charger. So the key takeaway here is simple. All electricity deserves our respect and a whole lot of caution. All right, so let's do a quick recap. Electricity is simply the flow of tiny electrons. It needs a push, which we call voltage, to get it moving. It has to travel in a complete loop, called a circuit. It moves easily through conductors, but gets stopped by insulators. And from this basic set of rules, we get the power to run our entire modern world. From Benjamin Franklin flying a kite to the phone or computer you're watching this on, our world has been completely transformed by understanding this one fundamental force. The next time you flip a switch, you'll know exactly what's happening inside the walls. So the only question left is, what amazing new thing are we going to power up with it next?